Good morning. Waiting for a few more people. Sí, practicamos juntos. Estoy leyendo un libro en español. Es muy difícil, tanto difícil para mí, pero voy a leerlo. Okay, let's go ahead and get started. So first thing, welcome to second semester. I thought you guys did a really good job on the final, so congratulations on the first semester final. People did better than I expected, frankly, because that was a tough exam, and people did really well, I thought. So pat yourself on the back for that. So regarding the second semester, we will we have kind of like 4 more topics to cover. And so the topics are simple harmonic motion, waves, electrical forces, and electric circuits. So those are the last topics. And then we'll prepare for the AP exam. So we'll have a midterm, the first triad, and we'll do our final at the end of the second triad. Okay? So I like to give my final early because that's when the AP exam is. So I'll give it right around the time of the AP exam, so that you only have to prepare once. I think it's silly to prepare for the AP exam and then, have a month off and then prepare for the final. Why not just prepare all at once? And then that last triad, we'll just kind of maybe do a project, do some fun stuff. Okay? So I'm going to go ahead and get started. So the first topic for second semester is what is called simple harmonic motion. Which I will often abbreviate as SHM. And so something is undergoing simple harmonic motion if its position as a function of time is sinusoidal. So sinusoidal means that it can be, it's like a sine or a cosine or a negative sine or a negative cosine. So any one of those trig functions, okay? So what that means, if you have horizontal simple harmonic motion, you have something that's going back and forth, This is horizontal simple harmonic motion. Okay, back and forth. So, for example, a pendulum undergoes horizontal simple harmonic motion. You can have vertical simple harmonic motion where maybe you have a rubber band and you tie a mass to the end of it, and the mass is going boing, 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 boing. So it's a sine. Their position as a function of time is described as a sine. It goes up and down and up and down. Okay, so so you have a position as a function of time, and it looks like this. Okay, so that's a sine or a cosine. This example is a sine. So what we notice is that the motion has a center line. So if we look at it, it's vibrating. In this case, it is vibrating. Another word I'll often use just as a synonym for vibrate is oscillate. It's oscillating about x equals 0. That's the center point of this vibration, okay? So if we look at how far does the vibration go from the center point, so we can see that it goes this far from the center point, or it goes this far from the center point. That is called A, capital A, which means the amplitude. So A equals amplitude. Okay. And it's basically how big is the vibration. Okay, so you could have a small amplitude. Okay, so that would be something like this. Or it could be a large amplitude, something like this. Okay, that's the amplitude. All right. I just thought of a really cool superhero name. It is Amplitude. The Amplitude. He can change his size. It's like Ant-Man, except it's a cooler name. The Amplitude. Okay. The other quantity that describes the motion is the time it takes to complete a full vibration. So if we look at this, it goes up, it comes back down, it goes back up again. This amount of time right here is called the period T. So the capital T is equal to the period, and it is equal to the time to complete a vibration. Okay, so if you have long period, looks like this, long time to complete a vibration. Short period looks like this. Okay, so this is a period that is small. This is a period, or I should say, we usually use short and long to describe periods. So short period and a long period. Okay, we don't have to use this method of getting the period. We could actually just do the time between peaks. That's sometimes an easier way to do it, that amount of time. Okay. One other possibility. So this is vibrating and oscillating about x equals 0. Okay. All right. But we could have simple harmonic motion about a different location. So what if we had something that was like this? So here's x equals 0 down here, but the oscillation is up here, okay? So we can see that it's oscillating about this kind of a center line, all right? And so I'm going to call that C, and that is called the equilibrium position. And that is equal to the position the particle oscillates about. Okay, so it's oscillating about a positive x value in this case. In this case, the amplitude would just be that distance right there. So the amplitude is the distance from that center line to the maximum point, or from the center line to the minimum point. Okay, so the amplitude is not from here to the maximum point. It's from the center line to the maximum point. Okay. So the general form of simple harmonic motion, basically your position as a function of time is going to be a cosine of omega t plus c. All right. So this kind of is our first main result. So capital A is the amplitude. All right. C is the equilibrium position. All right. This does not have to be cosine. It could be any trig function, or it could be sine or cosine, or negative sine or negative cosine. It wouldn't be tangent, because tangent is just a crazy graph that goes off to infinity, right? So it can't be tangent, but it can be sine or cosine. So it can be either one of those. And omega is basically related to the period. Through, and you'll want to write this equation down, the period is 2 pi over omega. Okay. So let's do an example and see how this works. Okay. So let's say you have your position as a function of time is minus 4 times sine of, let's say, 78t plus 7. Okay. So what we want to do is we want to figure out what is the amplitude, what is the period, what is the equilibrium position, and we want to graph it. Okay? And I'll graph it over here. So what we want to do is we want to compare this to x of t equals a cosine of omega t plus c. All right? And we just compare. All right? So just putting these things side by side, we can see. Now you might say, oh, the amplitude is -4. But that is not the case, because the amplitude is always a positive number. It's just the distance from equilibrium. So it's really the absolute value of this number that is multiplying the trig function. So that means that my amplitude is 4 meters. Okay. The period is 2 pi over omega. And we can see that omega is the number that is multiplying time. Okay. T is time, or lowercase t is time, uppercase t is period. And so we can see that 78 is omega. So 2 pi over 78 is going to be the period. Which is 0.08 seconds is the period. Okay, and then the number that is added on to the very end, that is the equilibrium position. So here the equilibrium position is 7 meters. Okay, so now we want to graph it. So I do my position in meters as a function of time in seconds. Okay, and I know that the equilibrium position is 7. Okay, so here's x equals 7, and that's going to be the center line of the vibration. Okay. So let me ask you this. If the amplitude is 7, or sorry, if the equilibrium position is 7 and the amplitude is 4, what is going to be the range of that vibration from what x value to what x value? Type it in the chat if you know. Excellent, 4 to 11. So that means that you can go 4 above 7, or yeah, 4 to 3. 11 to 3, that's right. So you can go 4 above 7 up to 11. Okay, and then you can go 4 below 7 down to 3. Okay, so that's what so here's the center line, here's the highest, here's the lowest. Now, how do we know what it's going to look like? Well, we can see that it's going to be a graph of negative sign. So positive sign looks like this, right? So negative sign is going to look like the opposite of that. Okay, so this graph, okay, looks like that. That's one full vibration because it's a back and a forth. Okay, so we know the time duration of one full vibration is 0.08 seconds. So this right here would have to be 0.08 seconds. Okay, and if we were to continue this for 2 vibrations like this, then that would be twice as long because each period is the same length. So that's going to be 0.16 seconds. Okay, so this shows how you go from an equation for the position as a function of time. Okay, to determining the amplitude to drawing a graph, okay? So now what we want to do is we want to go backwards. Let's try and do the opposite with the second example, okay? So here's the second example. It's going to take me a second to draw my position as a function of time, so bear with me. Okay. Okay. So we've got this. And so what we want to do with this problem, we have a motion graph that's representing simple harmonic motion, and we want to write the position as a function of time. Okay? So, so we're going to put this equal, and just for comparison, we have a cosine of omega t plus c. Okay, so it's going to have that form. So who can tell me, based on this graph, type it in the chat if you know, what is the equilibrium position? And once you tell me the equilibrium position, can you tell me what is the amplitude? Okay. And furthermore, can you tell me what is the period? So think about that for a second. I'll give you a moment to ponder. So very good. The equilibrium position, the center point of this oscillation is -5 meters. And we can see that it goes from -5 to +1. That's an increase of 6. And the it goes from -5 down to -11. That's a decrease of 6. So the amplitude is 6 meters. Very good. Now, just an FYI, because I see a lot of answers that are correct, but they don't have units. Units of equilibrium position are going to be meters. Units of amplitude are going to be meters. Units of period, because it's the length of time, are going to be seconds. Okay. So the period, it takes 0.6 seconds to complete a full vibration. All right. So what that means, okay, is that our period is related to omega by 2 pi over omega. So we have, so what that means is that 0.6 is 2 pi over omega, which tells me that omega is 10.5 radians per second. So the reason that this variable is called omega is because it has the same units as angular velocity. Okay, they're both measured in radians per second, so that's why that's omega. Okay, so I'm going to have A, which is 6, times a trig function of 10.5 t minus 5. So now we have the question of which trig function is it? Okay, And to figure out which trig function it is, whether it's sine, negative sine, cosine, or negative cosine, we have to look at the shape of this graph, okay? I know that sine looks like this, right? It goes up, then down. Negative sine goes down, then up. Cosine starts out high, like that. Negative cosine starts out low. So based on that, these four options, which of these four options does our graph represent? Type it into the chat if you know. It's quite a long delay today, as I'm waiting for you guys to respond. I guess while I do that, I will write down my next question. Oh, now everyone responded. So it's cosine, yeah. Because this starts out high and it goes down from there, so that is cosine. So cosine is our trig function, and this would be the answer for the position as a function of time. All right? So now what we want to talk about is what equation of motion will result in SHM. Okay? What equation of motion will result in simple harmonic motion? Okay? Another way of saying that is what equation has a solution x of t equals a cosine of omega t plus constant. Okay, so we're trying to figure out when does this situation arise. Okay, and so I'm going to give you the answer. The answer is the equation that will result in simple harmonic motion is minus omega squared x equals a. All right, so this minus sign is really important. This omega is the same omega that appeared earlier in the lesson. So period is 2 pi over omega. Okay. X is the position, and lowercase a is the acceleration. One thing I want to point out is that lowercase a is representing acceleration and uppercase a is representing amplitude, so these two are not equal to each other, so don't confuse them. All right? So if you encounter this equation, you will get simple harmonic motion. All right? And to see why, I want to remind you that acceleration is represented by bendiness of a position time graph. Okay, so let's try to understand why that's the case. Suppose I have a position as a function of time. All right, and what if that position starts out as positive? So here's zero position, here's positive, and here's negative. All right, so if the position is positive, if x is positive, well, let's look at this. Let's try and figure out what is the sign of the acceleration. So the acceleration is going to be a negative number times omega squared. Omega squared is going to be positive because when you square any number, it becomes positive. So we have a negative number times a positive number times the position, which is also positive. So if you have a negative times a negative times a positive, or a negative times a positive, you get a negative number, okay? So basically the lesson there is that when the position is greater than 0, when the position is positive, the acceleration is less than 0, okay? Having a negative acceleration means your graph is going to be bendy down. So your graph is going to go and bend down. Now, as a consequence of bending down, is it's going to bend down and it's going to eventually become negative. So what if x has a negative value? Then you would have a negative number times a positive number times a negative number. Negative times positive times negative is a positive number. So what that means is that when x is less than 0, the acceleration is positive, okay? So if your acceleration is positive, that means that your graph is bendy up. So it's going to bend up, okay? And then it crosses the axis again, and now x is positive, so it's bendy down. And then x goes negative, so it goes bendy up, and the cycle just repeats, and we get simple harmonic motion. So hopefully that explains how an equation such as this could result in a position graph that looks like that. So there's a relationship between acceleration and position that is true when we have simple harmonic motion, okay? So this isn't the equation when the equilibrium position is 0. If the equilibrium position is not 0, we have the equation minus omega squared times position minus c equals the acceleration. So this is the equation that will result in simple harmonic motion in general, okay? If I wanted to multiply the negative omega squared, I could do that. I could multiply it through this, and I would get minus omega squared x minus, or actually plus, omega squared c equals acceleration. All right? So let's do an example. All right? What if the equation of motion is minus 300x plus 75 equals 0.2a. All right? What we want to figure out is what is the period, and we also want to figure out what is the equilibrium position. All right. So the first thing I'm going to notice is that my equation for simple harmonic motion is of the form a equals something. It's not of the form 0.2a equals something. It's a equals something. Okay? So what I have to do is I have to divide both sides by 0.2. So I'm going to divide both sides by 0.2. And when I do that, dividing by 0.2 is the same thing as multiplying by 0.5. So I have, or multiplying by 5, excuse me. So you have, the equation becomes minus 1500x plus 375 equals a. All right? And the reason that I'm writing it over here is so we can compare with the equation of simple harmonic motion. So I have a and a. I have x and x. I have negative sign. I have negative sign. So that means that omega squared is 1500. Okay. And that means that omega squared C is 375. All right. So I can figure out the equilibrium position right away because I know that omega squared is 1500, so I can plug in 1500 for omega squared. And then I divide both sides by 1500, so I get 375 over 1500 equals, that equals 0.25 meters. Okay, so we get that the equilibrium position is 0.25 meters. That's the first part of our solution. Now we need to get the period. So we take the square root of both sides here to get square root of 1500 is 38.7 radians per second. And then we use the fact that period is 2 pi over omega. So 2 pi over 38.7 and we get 0.16 seconds. So the period is 0.16 seconds. All right. So what have we done today? We have defined simple harmonic motion. Simple harmonic motion means that your position as a function of time is sinusoidal. Sinusoidal meaning sine or cosine or any combination of the two. And then we learned about some different parameters that describe the simple harmonic motion, in particular the amplitude, which is how big is the vibration, the period, which is how frequent is the vibration, and the equilibrium position, which is what is it vibrating about. We learned how to identify amplitude, equilibrium position, and period from a position time or from a graph. And then we learned the equation that will result in simple harmonic motion. Okay, so we haven't talked about any specific simple harmonic motion system at all yet. We will do that on Friday's lesson. We'll talk about 2 simple harmonic motion systems. All right, so that's it for today, and I will see you in the Zoom.